Chapter 0 is not intended to be a review of linear algebra, but only of a few linear algebra results that will be particularly important in this book. Throughout this book, we will consider a vector to be an n by 1 matrix, that is, a column. So, for example, X transpose Y is a n by 1 matrix. X is n by 1 also, so X transpose is 1 by n, and the matrix product of a 1 by n and an n by 1 matrix is a scalar. So X transpose Y is really just the dot product of X and Y if X and Y are vectors. On the other hand, XY transpose is an n by n matrix because X is an n by 1 matrix, Y transpose is 1 by n, so XY transpose is n by n. One result that we'll particularly use often is this: the transpose of the product of two matrices is the product of the transpose in reverse orders, reverse order, much like the inverse of a product is the product of the inverses in reverse order. Of course, that assumes that A can multiply by B, that is, that the number of columns of A is the same as the number of rows of B. We'll use this result quite frequently. A couple of more minor theorems that we'll use in Chapter 1 at least. The product of two upper triangular matrices is upper triangular, and similarly the product of two lower triangular matrices is lower triangular, and also the inverse of an upper triangular matrix, if it exists, is upper triangular. We won't do the proofs in this video, just state the theorems. Another important result that really isn't a linear algebra theorem, it's a discrete math theorem, but we'll use it frequently in calculating the number of computations of an algorithm. 1 to the p plus 2 to the p plus 3 to the p up through n to the p is approximately n to the p plus 1 over p plus 1. For example, if p is 2, 1 squared plus 2 squared plus 3 squared up through n squared is approximately n cubed over 3. It's almost as if you're integrating, and that's not a coincidence because this series is an approximation to this integral. So when n is large, they're close to each other. So we'll be using this a lot when we encounter algorithms and we want to count the number of operations. Now a few definitions. A diagonal matrix is 0 except for the main diagonal. Tridiagonal matrix is 0 except for the main diagonal and the first superdiagonal and the first subdiagonal. In other words, aij is equal to 0 when the absolute value of I minus j is greater than 1. Now, these definitions don't tell you which elements are non-zero, they tell you which elements are 0. So for example, a tridiagonal matrix, all or some of the elements on the main or super or subdiagonals can be 0 also. In fact, the 0 matrix qualifies technically as a diagonal matrix or tridiagonal or upper triangular, but you wouldn't normally call it any of those things. An upper triangular matrix is 0 below the main diagonal. Obviously, a lower triangular matrix is 0 above the main diagonal. A upper Hessenberg matrix is almost upper triangular, but it has one extra subdiagonal of non-zero or possibly non-zero elements. We'll deal with upper Hessenberg matrices in Chapter 3 when we're trying to extract the eigenvalues. A symmetric matrix is symmetric around the main diagonal. In other words, aij is equal to aji for all I and j. a21 is equal to a12 and so forth. Now it's easily proven and well known from linear algebra that all eigenvalues of a symmetric matrix are real. A general non-symmetric real matrix may have complex eigenvalues because the eigenvalues, remember, are the roots of the characteristic polynomial, and a real polynomial can have complex roots. However, if the matrix is symmetric, the eigenvalues will always be real. A non-singular matrix is a matrix that has an inverse. That means, of course, that the matrix must be square, because non-square matrices can't have inverses. A square matrix will have an inverse if and only if the determinant is non-zero. A non-singular matrix, a matrix that has an inverse, is one in which the rows of A are all linearly independent, or equivalently, the columns of A are linearly independent. And of course, if a matrix has an inverse, then AX equals B has a unique solution for any B, because you can just multiply by A inverse. If A doesn't have an inverse, then AX equals B may have many solutions or no solution. A positive definite matrix, it's a definition we'll encounter frequently in this book, is a symmetric matrix, all of whose eigenvalues are positive. Remember, symmetric matrix, the eigenvalues are guaranteed to be real. If they're also all positive, then it's positive definite matrix. Now, there's an equivalent definition of positive definite, which is that it's symmetric and X transpose AX is strictly positive for all non-zero vectors X. Remember, that means since X and AX are vectors, that just means the dot product of X and AX has to be positive for all non-zero X. Those are equivalent definitions, not immediately obvious. Orthogonal matrices will be important in chapters 2 and 3. An orthogonal matrix is a matrix whose transpose is its inverse. In other words, A transpose A is equal to the identity, and therefore A transpose also equal to the identity. It's easy to show that an orthogonal matrix, the columns are mutually orthogonal and all have norm 1, L2 norm 1, and similarly for the rows. So the rows form an orthonormal set. The columns form an orthonormal set also, so it's a very special matrix. Now, we've just said that in this book we'll generally consider vectors to be n by 1 matrices. In this section we make an exception, and we will consider vectors and matrices very differently in regards to their norms. There are various norms of vectors, only 3 that we're going to use in this book. The L1 norm, the L2 norm, and the L infinity norm. For any p greater than or equal to 1, the LP norm is defined as the pth root of the sum of the pth powers of the absolute values of the components. So, for example, P1 simply means the sum of the absolute values of the components of the vector. P equals 2 is the usual L2 norm, the square root of sum of squares. Now, what about P equals infinity? Well, you can show that if P is extremely large, the LP norm is close to being simply the largest component in absolute value. So we define the infinity norm to simply be the maximum component in absolute value. Those are the only 3 norms that we'll use here. Now, the matrix norms are defined very differently. Even though the notation looks similar, the P norm of a matrix is very different than the P norm of a vector. It's defined as the maximum of the P norm of AX over the P norm of X. Remember that X and AX are vectors, so these are just normal vector P norms. And we're taking the maximum over all non-zero X. Obviously, if X equals 0, you have 0 over 0. So anything other than 0, it's the maximum over all X of P norm of AX over P norm of X. And immediately from this definition, you see that the P norm of AX is less than or equal to the P norm of A times the P norm of X. We'll use that frequently. Here, this means the vector norm, because AX is a vector, X is a vector. This is the matrix norm. Unfortunately, this is not a very useful definition in calculating the norm of a matrix. It would be very difficult to calculate the 1 or to our infinity norm of a matrix using those definitions because it involves the maximum over all of an infinite number of vectors. However, theorem 031 gives us practical ways of calculating these three matrix norms and proves that they're equivalent to the definition. The one norm of a matrix is the maximum column sum. That is, in each column you add up the absolute values of the elements and then you take the maximum of those. Not at all obvious that that's equivalent to the maximum of the one norm of AX over the one norm of X, but it is. The infinity norm of a matrix is the opposite. It's the row sum. That is, in each row you add up the absolute values in that row and then you take the maximum of those. The two norm of a matrix, which by the way is not the square root of the sum of squares of all the elements, the two norm of a matrix is the square root of the maximum eigenvalue of A transpose A. Now if A is not symmetric, the eigenvalues of A may be complex. However, A transpose A will always be symmetric, and at least the eigenvalues will be greater than or equal to 0, so you can take their square roots. This is the definition. Now if A happens to be symmetric, then this is just the square root of the maximum eigenvalue of A squared, which will just be the absolute value of the maximum eigenvalue of A. Finally, as an example, consider this matrix. The one norm, you add up the each column here. This adds up to 8 in absolute value, 6, 7. The maximum of those is 8, so the one norm of A is 8. The infinity norm of A, add up the columns. This is 8, 3, 10. The maximum of those is 10, so the infinity norm of A is 10. Calculate the two norm of A is more difficult. You have to form A transpose A and find its eigenvalues, which is the hard part. And the largest eigenvalue is 45.931. Take the square root of that and you have the norm of this two norm of A.